We are going to discuss capacitors. Capacitor is a device which is used to store electrical energy, or can say that it is a device which is used to store electrical charges. So, before we start capacitors, let's discuss what is capacitance. Capacitance is the ability of a conductor to store charges. As you know that charge, if it is given to a conductor, it increases its potential. So we can write that Q is directly proportional to V. If you add more amount of charge, potential will increase further. Now, if we remove this proportionality sign, we can add a constant of proportionality, and that is written as Q equals to CV, where C is capacitance. Or you can see that C we can write as Q by V, charge per unit potential. And if you take its unit, this is Coulomb per volt, and that we call it as Farad. Okay. Now, capacitance, as we said, that it is a capacity to store charges by a conductor. So, let's see that if you want to store more amount of charge, then you should have more value of the capacitance, because we can see that Q is directly proportional to V. So, let's go through the basic theory of capacitance. Let's suppose we have conductor A only initially, which we have connected to a source, and this gives a charge Q on the conductor. We have the charge, suppose Q on the conductor, and its potential then we can write as V equals to A. That is, potential in this case is potential due to the charge on the conductor A. Now what we are doing? We add another conductor B close to it. And if you add another conductor or bring another conductor B close to A, in that case there will be opposite nature of the charges developed on the nearer end and same nature of the charges at the farther end, making the potential now as VA minus VB plus VB dash. VA is potential due to the charge on A. VB is potential due to negative induced charge on B, and VB dash is potential due to positive induced charge on B. So this is the new potential of the system. Now we know that C, we have said that it is Q by V. Now you see, this VB and VB dash, if you compare, although they are due to charges induced on B, charges induced on B, that is the negative and the positive charges which are induced, they are equal in magnitude, opposite in sign, is still as the negative induced charges are closer to the system, so the value of VB will be more than that of VB dash. That is due to the positive induced charge. As a result, this V dash will become less than V. That means just by bringing another conductor B close to this conductor A, potential has now decreased, so capacitance will increase. That means the capacitance of this system we have increased. And if capacitance we have increased, that means we can store more amount of charges before the charges start getting discharged. Now what we can do if you want to increase further, suppose we earth B. If you earth this one, then positive induced charges, they will disappear. Why? Because electrons from earth, they will move and they will neutralize the positive induced charges, which are basically the free charges here. So they will get neutralized, and now the new potential will be your VA minus VB. So you can see that this potential VB dash is still smaller than V dash. So we have increased the potential or decreased the potential of the system, and hence we have increased the capacitance of the system. If you want to further increase the capacitance, you can add a dielectric medium between the two plates or the two conductors. As a result, the capacitance will increase further because the potential is inversely proportional to dielectric constant of the medium which is being introduced. That means the basic principle for the design of the capacitors, which will be basically a device which we can use to store electrical energy or electrical charges, will be to take two conductors and bring them close to one another and make the arrangement of the system so that it can store charges there. Now these two conductors which we are bringing close to one another, depending upon their shape, we have different types of capacitors. If the two plates which we have brought, they are parallel plates, then we get a parallel plate capacitor. If the two plates which we have brought, they are like one a cylinder and surrounded by a hollow cylinder or cylindrical sheet, then it is the cylindrical capacitor. If you have a spherical conductor surrounded by a spherical shell, then that will be your spherical capacitor. So these are the three types of capacitors: parallel plate capacitor, cylindrical capacitor, and spherical capacitor. Now, let's discuss the details of parallel plate capacitor. So, let's start expression for capacitance of parallel plate air-filled capacitor. We have taken two plates which are kept parallel to one another. They have the plate area capital A, plate separation is small d. Q is the charge developed on the two plates when it is connected to a source under potential difference V. E0 is the electric field between the plates of capacitor. Now, if you take the expression for electric field between plates of two plates of conductor, then this electric field will be given as E0 equals to sigma by epsilon naught, where this sigma is surface charge density and epsilon naught is the permittivity of free space or vacuum. Now, so this can also be written as your Q by A because it is the surface charge density, so we can write charge per unit surface area divided by epsilon naught. This is the expression for E0. Let's call this as equation number 1. Now we also have electric field written as V by D as electric field is equal to negative potential gradient. So E is equals to V by D, and that is basically E equals to minus del V by del R. So we can write this one as V by D because V we have taken as the potential difference between the plates of capacitor. Now, if you compare the two, then we can write from equation 1 and 2, Now see, from equation 1 and 2, if you equate, it is Q by epsilon naught A equals to V by D, or we can write Q by V equals to epsilon naught A by D. Q by V is the capacitance, because C is your Q by V. So we can write C equals to epsilon naught A by D. This is the expression for capacitance of a parallel plate capacitor. Okay. Now let's take another case. Now we are taking that between the plates of capacitor, some dielectric have been filled. So this is the expression for capacitance of parallel plate capacitor with a dielectric medium between the plates. Now we'll try to find out expression for capacitance of parallel plate capacitor with dielectric medium between the plates. Now for that, we have shown we have the two plates of the capacitor. Between the plates of capacitor, we have dielectric medium of dielectric constant K. A, as usual, is the plate area and D is the plate circulation. This is connected across a potential difference phi. So now let's just make the changes in our previous derivation. Now this will be electric field E between the plates of capacitor, which will be equal to sigma by epsilon, not epsilon naught. And this can be written as your K times epsilon naught, where K is the dielectric constant. So now here there will be another term, that is K there. Again, the electric field E, this time it will be your V by D, as E is the negative tensile gradient. So we can write this, if you equate equation 1 and 2, you can write equation 1 and 2 as Q by K epsilon naught A equals to V by D, or it is K times this. So C will be equals to K times epsilon naught A by D. And if you just compare with the previous expression, this is your K and this is your epsilon naught A by D. This we can write as K times C naught, where C naught is capacitance of parallel plate air-filled capacitor. So this is the expression for capacitance of parallel plate air-filled capacitor with a dielectric medium between the plates. Now, you just must have noticed, I have not rubbed the derivation which we have done in the previous case. Just to show you that derivation of the two is not different, just you have to make little modification in the expression, like instead of E naught we have used E. So we have written now this as sigma by epsilon, not epsilon naught. So just our term K, which is the dielectric constant, have appeared in this expression, and we can get the entire derivation. So if you remember the steps of derivation of one, you can easily get the expression for derivation for the second one. Okay. Now just we'll go for the next derivation, that will be expression for capacitance of parallel plate capacitor with a dielectric slab between the plates of capacitor. So let's do that one. Let's take that between the plates of capacitor, having plates A, plate area as A and plate circulation D, we have a dielectric slab of thickness T put between the plates, and K is its dielectric constant. Suppose the V is the potential difference across the plates of the capacitor. E naught is electric field in the air gap, and E is electric field in the dielectric medium. So now, if you take the expression for potential difference here, then this will be equals to E naught D minus T plus E into T. Because E naught we are using as the electric field in the air gap, And if the plate separation is D, thickness of the slab is T, so effective air gap will be only D minus T. And for the potential difference across the slab, we have E into T. So this can be written as E naught D minus T plus E naught by K into T, as K is E naught by E. Okay. So here, this E naught, we can again take it outside. Now, up to this expression state, I think it is clear. We have just taken E naught outside. So it is your E naught D minus T plus T by K. And E naught we can write as sigma by epsilon naught. So this will be your D minus T plus T by K. This again can be written as Q by A into epsilon naught, which is D minus T plus T by K. Now, all this was equal to V. So now we can write Q by V equals to epsilon naught A this is Q by V, which is equal to C. So this is your C. That means expression for capacitance of parallel plate capacitor with a dielectric slab is epsilon naught A divided by D minus T plus T by K. This is the expression which we can use for all different cases. Whatever be the slab thickness there, or we can take this one for a very thin slab there, or let's apply this one to another case when we replace dielectric slab by a conducting slab. For parallel plate capacitor with a conducting slab, if you apply the same in this expression for the dielectric slab, for conductors, we know that value of dielectric constant is infinity, because we know that E is E naught by K. And electric field inside a conductor is 0. So as this is 0, it is your E naught by K, or K will be your E naught by 0, that is infinity. So if you apply that one for this case, this will give us epsilon naught A by D minus T plus T by infinity, or epsilon naught A by D minus T. This is the expression. So we can use this one for capacitance of parallel plate capacitor with a conducting slab. Remember that this can be used for any cases. That means this we can use as a general expression. Let's take case 1. If T is 0. T is 0 means the thickness of the dielectric slab, we are taking it as 0. If thickness is 0, that means there is no dielectric slab between the plates of capacitor. So it is as good as an air-filled capacitor. So if I put in this expression, it will be C equals to epsilon naught A by D minus 0 plus 0, which is epsilon naught A by D, which is the expression for capacitance of parallel plate capacitor with air between the plates of capacitor. So this is the same expression which we have derived earlier. Let's take case 2. If T equals, or if suppose T equals to D, that means slab is completely filling the gap between the plates of capacitor. So it is as good as capacitance of a parallel plate capacitor with a dielectric medium between the plates. So if I put it here, C will be equals to epsilon naught A by D minus D plus D by K, or it is K times epsilon naught A by D, which is exactly the same expression which we have got for capacitance of parallel plate capacitor with dielectric medium filling the gap between the plates of capacitor. So these are the different cases which we can get, and this is the expression which we can use it as a general expression so that you can apply it for any case there. Now, as we are saying that capacitor is a device which is used to store charges. So if you take the different cases there, which is the best capacitor? Obviously, best capacitor will be one whose capacity is infinity or maximum. So in that way, you may be tempted to say the case of the conducting slab where if the conducting slab is completely filling the gap between the two, then C will be equals to epsilon naught A by D minus D, and that is infinity. That means the capacitance of this capacitor will be infinity. But if you take it in a general case, this capacitor is of no use. Although capacity is infinity, but it is of no use because it is basically not storing any charge. It is as good as you have a bucket. We have the bucket of different capacity. If we have a bucket of 25 liters, that means it can store water up to 25 liters. After that, there will be overflow. If you have a bucket of 50 liters, that means it can store water up to 50 liters. But if I take a bucket without base, theoretically there will be no overflow. So that way its capacity will be infinity, but that is of no use. Same is the case when you have a capacitor and the plates between the capacitor is filled with a conducting medium, then it is not storing any charge. It is simply transferring the charge from one plate to another. That is why the capacity is infinity. Why it is infinity? That also you can understand from the expression. It is Q by V. As the two plates will be at the same potential, so potential difference will be 0. Both are at the same potential. So in that case, this is your Q by 0 and this is infinity. So this is all for the capacitors and different cases of capacitor if you take a parallel plate capacitor there. Thank you.